Hello, my name is Chris Alikas, and welcome to Kitchener-Waterloo Video Tech Meetup on November 30th, 2022. We're visited today by Luc Trudeau. I met Luc at DMUX this year, and we started talking, and he's out in Montreal. And I was saying that we have a pretty neat Kitchener-Waterloo Video Tech Meetup that we started from DMUX, and I asked him to give a little talk today. So Luc's a video compression researcher at Two Orioles, and he's also a volunteer contributor to the David AV1 video codec. So Luc, take it away. Thank you.
All right, thanks for the intro. Yeah, exactly. So tonight I wanted to talk a bit about kind of a pragmatic approach to objective and subjective quality assessment. Now, I understand that previously there's already been talks about this. So I've put them in the slides here. Basically, if you haven't seen these slides or these talks, basically my talk is going to be a bit different. So they're not a prerequisite, and they're also they're not the same, right? So don't worry about it if you haven't seen them. If you haven't, you can go see them after this talk. And if you did, well, it's gonna be a bit like a different view of a similar topic. There's also a talk about banding, I think I saw in your previous content. That one maybe a little less, but more of these two talks I think are really relevant to what we're going to talk tonight. So my objective here is basically, and I think you've probably all had this situation where you have, your source image, you have a disrupted image, and then a bunch of numbers next to it. And we all know these numbers. We all know their name. Some of them are more famous than others, but maybe we don't know exactly how to interpret them or how they're computed or what the values actually mean. So, and that's what I want to go over tonight with everyone. So basically just get a good feel of what these values are, where they come from, and how we can better understand how to use them. So, the video, let's hope it works. So I would like you to think of an image tonight as a surface, a 2D surface in 3D. So something like that, right? So imagine that all the pixel values are, the height of different points along a surface, right? So you can think of this image of the tiger here as this representation. That's going to help us a lot in understanding how metrics work, because when we add in our distorted image, we now have two surfaces, and we end up with a volume between them. This is going to be a bit hard to see, so just imagine it really hard with your imagination. But you can see that in the part where the images are the same, so the top part here, this is flat, there is no volume. And then the volume starts to appear when the differences start, right? And hang on, there you go. So what we want to do is we want to quantify this volume, right? So, and there's kind of two different ways to go about it. We can actually try to find out what the exact volume is, and that would be kind of an objective metric. So we're going to find, exactly one number, and it's going to give us what that is. And then the other way we can go about this is think, well, what would be the human perception of this volume, right? How would this volume be annoying to me or to somebody watching a video? And that's going to be the subjective path. So we're going to start with the objective because that one's a bit more concrete. Subjective is going to be a bit different. So objective image quality assessment. So we have our two surfaces here, again, on the same plot. So one is the image, the other one is the broken image. And we would like to really get this volume figured out or get a number for this volume. So there's kind of two equations that you can use. You can use the mean absolute error, or you can use the mean squared error. So usually we'll use the mean absolute error when we actually have to do a lot of processing because it's faster. Whereas the mean squared error is a bit slower, but then the advantage of that one is that because we square a value, so for example, if I have 5 differences of 1, well, the square of 1 is still 1. So that will just sum to 5. But if I have 1 pixel that's off by 5, then the square of 5 is 25. So the MSC will be more sensitive to bigger values or bigger differences. And that makes sense because our eye is probably going to be drawn more to bigger differences than smaller ones. So while these are very popular, I think the most popular one that everybody loves or loves to hate is the PSNR, right? So PSNR is kind of a weird metric in that everybody uses it. A lot of people's bonuses are related to it, but everybody will say, well, don't use it. You know, you shouldn't be using it. And then they'll turn around and give you this presentation with PSNR all over the place. So I think the problem is that there hasn't been this like one metric that takes over and solves all the problem in PSNR and has no flaws, right? So what ends up happening is we just measure a bunch of different metrics and then look at all these different metrics. So what is peak signal to noise ratio? So maybe some of you are used to using it, but may not understand exactly what it does. So I put the equations here. So the question is, like, what is this peak signal? Is it peak signal to noise ratio, or is it peak signal to noise ratio? Like, how does that work? So if we look at the equation, we can see that there's this max component, and that's going to be the maximum value of your bit depth. So for example, tonight we're going to be working with 8-bit video because it's simple. So the maximum value there is 255. So this is going to be 255 squared, okay, over the mean squared error, which I've talked about before. And then you do 10 log 10 of that, and that gives you the final score. So it's easy to map PSNR to MSE. So I've done this here. So this is the entire range of PSNR and MSE. But usually when we use it, we'll only use kind of from 50 to 20. Below 20 is considered really bad quality. So I've blown this up here. You can see this is usually the part we'll use. So from 50, which you can see is almost 0 MSE. And then as the MSE goes up, we see that the PSNR goes down. Right? And I've put some numerical examples here if you want. So if we look at the first one, you have a mean absolute error of 2. That means that overall of my image, there's going to be, on average, the pixels are going to be off by 2. So that actually makes sense. I can understand that. Mean squared error of 4 is that value squared. And then PSNR related to that is 42.11. So what I like about this is it gives you a feel for each of the PSNR value, what would be like on average the offset for each pixels. You can see that here. So what are the extreme values of PSNR if I want to understand it better? Well, so usually you'll have infinity, and infinity, that'll mean that the two images are the same. Some APIs you use PSNR, they'll cap it at like 100. So if you see a PSNR score of 100, that might also mean that the images are perfect. So that's usually well known. The other one, what's lesser known is what's the worst PSNR value you can do? Is it possible to hit 0 dB? So it is possible to hit 0 dB, but that would be if you'd have like an all black image going all white or an all white image going all black. If you have intensity values, then it's impossible to actually hit 0 dB. So I've written this little script here that produces the worst possible PSNR value just for fun. So you can see it in action here. Basically what you do is you look at the pixels, and if they're over 128, then you set them to 0. And if they're below 128, you set them to 255. So this is exactly what you see here. And this creates, so if we remember our surfaces from before, so we create the maximum distance between the images that we can produce. So the biggest volume possible. So we see this here at 2.49 or 43 dB, which is the minimum score you could get with this image. And just to give you an idea, that's a mean absolute error of 188. So for each pixel, you're off by 188, which is a lot. But that's completely useless, but interesting nonetheless. So what's a common mistake with PSNR? So if there's one thing I can share tonight to don't do with PSNR, it's this. And it takes multiple forms. So I'm going to give the canonical example, but you've maybe seen this before. So let's imagine you're at a show or something and you're taking a picture or you're taking a video with your phone, and that phone has like a hardware H.264 encoder, right? And then So we're the engineers working on this platform, right? So we're making this possible. So we measure the PSNR and the MSE. So we compute it. So the source, and then the encoded image with H.264, and then we get the PSNR score of 20.20 dB. And now we have our encoding pipeline, and we decide to add in AV1 because AV1 is so cool and so awesome. And we decide to measure, what goes in our pipeline and then what comes out as AV1, and then we measure 33.80 dB. And we do this using the H.264 sequence because maybe we threw out the reference, we don't have it anymore. And then we can go around to conference and saying, look, so great, we've got 10 dB improvement from one image to the other, right? Isn't that awesome? And turns out that makes no sense. You can't do that, right? So this is like a common mistake I see. Like the AV1 here is not giving you 10 dBs more. What happens is, and if we remember our surfaces from before, is that you're not comparing to the same surface anymore, right? So what you should be doing is measuring from your AV1 image to your reference image. And then you would get a score of 22.19. And that's about the same as 22.20. So you have the same image, right? Now you'd say, well, wait a second, AV1 is supposedly so great. Why can't it do better than H.264 in this case? Well, the thing is that the image or the quality was lost in the encoding phase of H.264, and you'll never get it back, right? So there's nothing AV1 can do. There's nothing no encoder can do to bring that back. That quality was lost, right? So when the AV1 encoder is going to run, it's actually just going to take whatever it has as the reference, in this case, the H.264 stream, and it's going to do the best it can to encode that and give you the best quality possible, but it can't go over what the other one was doing. So then you say, well, what's the point then? Why would I use AV1 in this case, since there's nothing better than H.264? Well, then we're going into encoder discussion, so I'm going to keep this brief, but the idea would be that the file size would actually be a lot smaller for AV1 than it is for H.264. But AV1 can't bring that quality back. So that's just the thing to consider. When you're using PSNR, you need to, if you're comparing two scores, they need to be from the same reference, right? And if you are using distorted or broken references, like is the case here, then it's very important to know that you'll get higher scores because your reference, that starting degraded reference is going to be your starting point. So that's going to be your infinity. And then going down from there, you're going to have the other values. So keep that in mind. That was just one of my pet peeves I often see. So going back to maybe a little less useful, but still very interesting topic about PSNR. So I was musing with this idea of, could it make sense, or is it possible to generate like a series of images or a series of frames that would have exactly the same PSNR score? And it turns out it's very easy to do, right? I thought I'd go over this with you. So you start with your noise. I'm sorry if you can't see this well. This is just a normal noise pattern. So some Gaussian noise, I think. And then you inject it into your first image. Now, when you're going to inject the noise inside the image, it's going to saturate some pixels. And that just means that if your pixels are capped at 255, when I add in the noise, I might go over. So what I'm going to do is I'm going to just clip all the values where the noise causes saturation or where it causes the value to go below 0. And then I get a new noise pattern. And then I'm going to take that noise pattern, inject it in the next image, and then do that clipping game again to make sure that I don't saturate any pixels. And then what I do with that final noise is I can apply it to both of these images, and I'll get exactly the same PSNR score. Because we've talked about this, it's just the distance right between the two surfaces. It's that volume, and I've created the same volume just starting from two different places. So you could do that as many times as you want. I did it 8 times here. So all of these images here, and you might remember these images because these are the images I asked you to rank for tonight. So By the way, we've had 29 people fill out the form, so I'm super happy. Thank you for that. And we'll get back to that later. But the idea of all these images I've shown you in that form are exactly the same PSNR score. They're 27.97, all these numbers here. They're exactly the same. And you say, well, how can that be? Well, because the surface, or the distance between the surface, is the same. So that's what I did here. And it brings us to this next point, that while PSNR might not care about the source image, we as observers actually really do care about it. And for us, all these distortions aren't equal, they're different. And that's the topic of subjective image quality. How do we get a bit of human feel into this equation? How do we measure this in a more human-friendly way? So I've talked about this before. PSNR doesn't really care about where the error is in the image. It could be anywhere and it would still give the same thing. It only cares about the difference between two images. Now, humans, we actually care a lot about the source image. If we see the same error in different images, we're going to think it's different. And the reason for that is that parts of the image could actually have an impact on how we see error. So two phenomena that are very well known is, the first is called contrast masking or activity masking, and the second one is intensity masking. So we're going to see how the image in itself can actually mask away some of the error. So contrast masking or activity masking is the idea that if I take the same amount of noise and I apply it to an image, well, when you're going to be in the flat area, you're actually going to see more of that noise. And when you're going to be in a textured area or a busy area, you're going to see less of that noise because the natural texturedness of the image hides some of that noise for us. So if I want to make a metric that needs to take into consideration contrast masking, then I need to measure where the contrast is and take that into consideration. The other one is intensity masking. And intensity masking is the idea that the more intense or the brighter the image is, the more the step you're going to need, or the difference you'll need to create a perceptual difference, is going to be higher. So let me try to explain that clearly. If you look at the black image here, or the dark image, we can actually see that noise pattern very well because it's smooth. We talked about that before, but it's also very dark. Whereas here, there's also smooth areas, but the image is very bright, so we don't see the error as much. So this is a case of the error, the image actually masking some of the error for us. So how do we actually take this into consideration? Well, we're going to look at SSIM here, because SSIM actually, compared to other metrics like maybe VMAF, we can actually reason about what SSIM does and understand what it does, whereas VMAF is more like a neural network, so then we can only assume what it does. So SSIM is interesting here because we can see the difference between a metric like PSNR and a metric like SSIM. So SSIM has three different metrics or measures it has. It'll measure luminance, it'll measure contrast, and it'll measure structure. You can see those as L, C, and S here. And you can see these little alpha, beta, and gamma values. We'll get to those later. For now, just assume they're not there. So let's start with luminance. So luminance, that makes sense. We've talked about it before. You know, the intensity in an image can actually have an impact on how we perceive it. So SSIM, what it's going to do is it's going to go over the image in blocks of maybe 8 by 8 or 11 by 11, depending on the implementation. And it will compute the average of the intensity. And it will just compare these two together. It does it this way here. Now, this might look like some very complicated math function, so I'll try to break it down so it's very easy to understand. First of all, the C here, we can just ignore them. We're going to see a lot of C's in the next equations. They're always just there, so we don't divide by 0. So they don't actually have a big impact on the behavior of what's going on, so we'll just ignore these. Now, this thing here, this is actually a very complicated way of making a ratio that goes from 0 to 1. Well, not very complicated, but something that looks complicated. Actually, what happens is we have, imagine that X and Y is the same image. So in this case, you'd have 2 mu x, and here you'd have mu x squared plus mu x squared. Well, mu x times mu x is mu x squared, so 2 mu x squared or mu x squared plus mu x squared is the same thing. So this is just two ways of writing. If these two are the same, then this is going to be the same value over itself, so it's going to be 1, right? If you have 10 over 10, it's 1. If you have whatever value over whatever value, it's always going to be 1. Now, as these values become different, as these images change, then this ratio is actually going to go away from 1 towards 0. That means like 0 in this case would be very, very different. Now, so that's how we understand luminance. Let's have a look at contrast. So contrast, the C are still there. We remember those, so just ignore those. And now we see that instead of using average, for contrast, we'll use standard deviation. Now, if you don't remember what standard deviation is, just think of it as you take the average, and then you look at the difference with the average. So you do that over your block. And then we see the same pattern here of 2 multiplying two things here with something squared plus something squared here. So it does exactly the same thing as before. If the standard deviations are the same, then we're going to have 1. And if they are different, then we're going to go away from 1 towards 0. And that's how we understand contrast. Interesting note here, you're using the square of the covariance. That is just simply, the square of the standard deviation, that's just a variance. So next for structure. So structure uses covariance. So covariance is just the product of the deviation between two different values. So we see it here, and we have some C values, so C3, we just ignore those. And then we have the covariance of x and y over the standard deviation of x and the standard deviation of y, and this works exactly the same way I explained before. So if they're the same, we'll get 1, and if they are different, then we're going to go towards 0. So that's how that works. So let's see it in action. We got our image from before, and now we see this huge string of ratios between 0 and 1. So how does that work? Well, in this case, we can break it down. So let me break this down for you. So here I've separated all the values by luminance, contrast, and structure. And we see that, so this actually is called MSSSIM. So SSIM itself is usually resolution dependent. And when we want something that's resolution independent, you'll use MSSIM. Now, this might be a bit confusing because usually when people talk about SSIM, they usually mean MSSIM. But they are two different things. So in this case, we can see that it basically takes the original resolution of the image, and then it'll just break it down by like half a resolution every time. And for luminance, it's important to note that we'll just take the smallest of the resolution. So these will always be set to 1. And then for contrast, then we do it, we measure it for all the different resolutions. So you can see all of the chains here. So from before, if you multiply them all together, you get your final SSIM score. And just that's how simple it is. And that's interesting of a view also because you can see how luminance plays a role, contrast plays a role, and structure plays a role in the analysis of this image. So if we take all our images that we had before, now remember these images had the same PSNR, and we look at how MSSIM will rank them. We can see them ranked here. I can go over them quickly if you want. So here the best one is the Los Angeles frame. So it's at 0.87. Now that's something important about SSIM. These values are not percentages. You can't say 87%. That's another common mistake I see when people are talking about this. We've seen this before. This is just a multiplication of a bunch of different ratios from 0 to 1. It is not a percentage, and there's not even a linear scale about this. So you can't say if something is 0.5, then it's twice as worse as something that was 1.0. So just keep that in mind. These scores aren't on a linear scale, and we can't interpret them like percentages, even though a lot of people will do that. So we see here. So the second best image is the driving image. So 0.84 on the score. We can see the breakdown between luminance, contrast, and structure. I'm going to go quickly here. So this one is 0.81. Again, we can see the breakdown. The car scene. We can see the breakdown again. .77 here, and we can see this breakdown. So this is one I'm a bit surprised of, because to me it seemed like it was hiding the error very well, but structurally SSIM really doesn't like this image. So, and then this one, we talked about it before, because it's so dark, it's very easy to see all of the noise compared to the other images. So I think this comes into in the contrast term. One thing I was thinking about in this one, so we do have some experts, SSIM experts here. So I'm just gonna float this one up here. But I was wondering, since all of this is 0, right? Then you're doing your covariance. Then you just end up with a bunch of products times 0. So I'm guessing this all goes to 0. But I haven't taken the time to actually look that happened. But I figured since I was here, and some people might know, I'm just going to float that there.
So that's why the stability constant comes in, because you cannot totally ignore it. So that's the reason.
Yeah, exactly. Yeah. So the C constants that we talked about before, so C1, C2, and C3, yeah, you don't want to divide by 0. So I totally agree with that. I think the question was more, since you're doing the covariance, then you're multiplying things by 0. So maybe you're not actually, like, it's canceling the other term that it's multiplying with. That was my question. And the window, I think this, to me, this is the one that looked the worst. And SSIM really says this one is really bad. So how does this compare to the votes that we have? So thank you for everyone for voting on this. This is not your standard MOS experiment. So this is not how you would do, your objective image quality assessment. This was just, for the purpose of this talk, we're just going to rank them and have this kind of nice effect here. So basically what I did, I just looked at each of the sequence. You had a chance to rate them from 1 to 8. So the idea was to kind of sort them for me. So 1 would be the best, all the way up to 8, which would be the worst. So then all I did was just add up all the scores I got from everybody who participated. That was fast, so I could do this right before the meeting. And it basically gives us a sum for all the different images. And then I just sorted them by which of the images had the lowest score to the highest. And then I wanted to compare that ordering to so this is the KW Videotech ordering to the MSSSIM ordering, as an idea of how that works. So, and I think everybody agrees that this image is the worst one. The ordering isn't exact, but I think we definitely see some patterns of things that, both SSIM and K Videotech didn't like, but maybe not in the same order. But again, this has no scientific value. Please do not interpret this. It's mostly just for, understanding and having an idea. Again, what I want to push with this is remember that PSNR is exactly the same for all of these metrics, all of these images, sorry. And then we can actually sort them differently if we use subjective approaches. So that's it for me. Thank you for your attention and your time. I'll be glad to take some questions if you have any.
Now it takes way more sense why we were rating what we were rating. I had lots of questions that I sent to Chris, but all of those are answered after attending the talk.
Yeah.
Sorry, go ahead, Chris.
Oh, I was just saying, I really liked the I really liked that they're all the same PSNR. But maybe Abdul can answer this too. But what is a good MSSIM score? Like, is it anything above like 9, like 0.9?
Luke,
Right.
you want to answer or do you want me to answer? Go ahead.
Well, I mean, so I was going to say there's actually some scaling functions that you can use if you want to actually scale that score to a MOS. And then after that, it's mostly probably application specific. So for some cases, you'll see some people put the bar at 0.95, other people put it at 0.9. So and again, some other people think it's percentage. So I've seen some weird things that you shouldn't be doing. So there is this one post, I tried to find it before the meeting, before this talk, couldn't find it, where somebody was multiplying SSIM with PSNR. And that's so that makes no sense.
Yeah, generally, so it's non-linear, as Luke said, with subjective quality. It drops faster and then drops lower. So 0.95 is what I would say, Luke. I mean, like you said, then it starts dropping faster. The issue is that it's not linear when it comes to, or aligns when it comes to different types of impairments. So in case of noise or grain that you have added, it would drop much faster. So your threshold has to be relatively lower if you're equating it to compression. But for other impairments, it may drop relatively slower. So it's not cross distortion normalization that's happening here. Because metrics generally don't do well for texture preservation. Humans look at it a bit differently.
Are there any other questions?
I'm wondering, Luke, if you have read the paper on something called MAD competition.
Nope, I haven't read that one.
So let me share the link here. That could be quite interesting, relevant to the talk here. So that's a way to create, using the same image, create derivatives of the image with the same MSE or same SSIM. And then you can compare visually if for the same, so you keep one metric the same and then you modify the other metric the most you can. And that's way to compare metrics. And this has been improved to something called group MAD competition that was done recently, like 3-4 years ago. So you can keep one metric the same and then create extremes for the other metric and see visually if they are extremes or not. So this page talks about that, how to mathematically create using gradient descent or descent and differentials of different metrics.
Right. I think that's basically the gist of that I had when preparing this talk, because I wanted to something that would be easy to communicate with people and that would grab their attention. So that's definitely along the same lines. I did play around with something like that for SSIM, but it's not far along for me to present it yet. But the idea was the same. Could I have this box that could generate all these images that have exactly the same SSIM score, and then from there, have people rate them or see how much they can change.
Yeah, that makes sense. With this approach, you can do the reverse, create images with the same SSIM and compare the PSNR values. So that also can be done.
Yeah, exactly. I was going to try some like brute force thing, or just like,
I see.
do a bunch of computation and then just pick up all the SSIM scores that are close to one another and then use that. But it would be fun if there was a mathematical way to produce something that has, like, I don't know, 15-digit precision of SSIM, equality. So there's not much of an application for it. It's just for fun and to have myself like a better understanding of how this works. Right? So this usually starts from me wanting to, better understand things, and then writing up these crazy scripts.
Yeah, no, it certainly is a good way of comparing metrics and thinking of. We obviously agree, which is why I've written papers on it.
Yeah, that mad computation stuff looks really cool, so I'll look into that. Any other questions? Was the level of this talk like too high, technically too low? How would the gauge be there? Like, I know Abdul has a PhD in that, so he's like, this is way too low. But for everybody else,
I like the visualizations of the errors and things like that at the beginning, and sort of thinking about it a different way. Something like, we've thought about for a long time or used for a long time, but just having never maybe really thought too deeply about what it means. So I appreciated that.
Right, thank you. Yeah, that's definitely the objective I was going for.
Yeah, I'd say it was a good level for me. I do appreciate the trick that of making them all the same PSNR, because I remember when I went through and rated them and said, why are these all so awful? Well, now I know.
Yeah, exactly.
They're all exactly equally awful by one particular metric. And you're right. It was a good demonstration of how I didn't rate them the same, because I rated them according to how much the error damaged my impression of the image. So like the one street scene where I remember the one label went from solid black to solid white, but it was fine because I could read it either way. There was another scene where it sort of turned into noise and you couldn't hardly read it at all. That's obviously much worse to us. But the metric sees no difference.
Yeah, I think it's also another point that I didn't stretch much, because it would lead to like 10 other slides, is the fact that these metrics are actually color blind. So they don't see the color points. And then if we go into color, that's a whole other presentation. But yeah, there's definitely something there that there are ways to do SSIM with color. But it gets complicated. I think there's not generally a consensus on how to do it. I've seen people just do it across all the different planes, but then if you think about it, you're computing your luminance, and I don't think that makes sense to do it. But it has been done like on different planes.
Yeah, you wouldn't want to treat all of them the same either, because your resolution for luminance is about 10 times better than your chrominance only resolution. But still, the color does matter. And the other thing that is not addressed at all by many of these metrics is temporal. You say, oh yeah, all these images are this good, this faithful representations of the original. But if in fact all of them, if each image was vastly different from its previous one by being different from the master in the opposite direction, you'd really notice that. And yet any single image, you wouldn't see it. They may have all exactly the same PSNR, but relative to the one before it in sequence and the one after in sequence, they'd be very, very different and very, very obvious.
Yeah, exactly. I think VMAF has a temporal component, but yeah, SSIM. But I think there are also variants of SSIM that have like temporal pooling, but that's not something that's covered here. And I think that's also the other thing that's, I think a lot of people just use 5% of SSIM in that, they use MSSIM, that's it, no color, no temporal pooling, no nothing. But they did add a lot of other work related to that. So I guess at some point we'll need to raise the bar of what we use.
I'm resisting hard not to talk about Simplus, and I'll leave it outside.
Well, yeah, that was kind of the other, I guess the plus for me was I'll make an SSIM talk and show it to you guys just for fun, just to poke and provoke.
I
That'd be
wonder.
fun.
I wonder. I know, like I've seen the Meridian sequence a bunch of times, and I wonder if the familiarity with what I expect the originals to look like impacted my ranking of the images versus like some set of content where I've never seen it before. So I'm not sure how many people in the call have seen Meridian, but I have before, and so I'm pretty familiar with.
Yeah,
the
so I
entire
did include
sequence.
the reference, right? So if you in the form, the first image was the reference, and then the second was the
Oh, yeah.
distorted, right? So
Yeah.
so it was always relative to that, right? Because I didn't assume that people would see it, like unless I was going with Big Bug Bunny or something, I wouldn't assume people have seen it.
Yeah, that's fair.
But yeah, I mean, going back to Simplus, like I would be curious to see how it rates. Like you have the images in the form, you can try it out and give me the Simplus ordering of these images.
Do we have the downloadable versions of these?
Yeah, you're right. Maybe the form manipulates the JPEGs or converts them to JPEG. I have PNGs. I can give them.
Yeah.
Yeah,
Okay.
I
Sounds
can
good. That
make
would
them
be fun.
available.
Yeah.
Yeah, I also I could make the scripts available. Also, I'm just not sure if there's any interest. So, and they're not super clean. My Python skills are not great.
So if there's no other questions, I guess thank you, Luke. That was a really fun talk. It definitely the twist of them all having the same PSNR. It really
Mhm.
it was really fun to see that. So yeah, thanks everyone for coming. Thank you, Luke. Probably no meetup in December. So everyone, if I don't see you all again, hope you have a good holidays, happy New Year, and we'll come back in 2023.
Thank you. Merry
You-
Christmas and Happy New Year to everyone as well.
Yeah.
This was great. Thank you.
Thanks.
Yeah.
Thank you. Bye.
Okay,
Bye.
thank you.
Thank you.
Take care. Bye.
Thanks for having me on.
Yeah. Thanks, Luke.
All right.
Enjoy your night. Bye.
You too. Bye.